Okay, so let's continue example 3 from section 5.4. We found those derivatives in the previous video. Let's go ahead and continue. So in the next thing on our list here, find the roots of the function and the y-intercept. So let's do that. Y-intercept, remember how we do that? We find f of 0. So f of 0. Well, if I plug 0 in there, I'm just going to get 0. So f of 0 is 0. Our y-intercept then is at 0, 0. Okay, now it turns out that since the y-intercept is 0, 0, that means the x-intercept also is 0, 0. And you can find that by just setting the whole function equal to 0. But really, all you need to do is set the numerator equal to 0. If you set the whole thing to 0, then you can just multiply both sides by the denominator. Well, 0 times anything is 0. So really, all you got to do is just set the numerator to 0. So x equals 0. And of course, that means we've got the same x-intercept as we do y-intercept. Okay? Only one. Then we want to do vertical asymptotes, horizontal asymptotes. It turns out that for this function, there are no vertical asymptotes. How we would find them is we set the denominator of the function equal to 0. But we see what happens if we do that. I'm going to get x squared equals minus 4. Well, you can't square anything and get a negative number, so there's none. No vertical asymptotes. Okay, horizontal asymptotes. There is one of those because remember how we find the horizontal asymptotes? We take the limit as x approaches infinity for our function 4x squared over x squared plus 4. Now remember how we deal with limits like this. The degrees are the same, second power in both the top and the bottom. So the limit is going to be the ratio of the leading coefficients. 4 over 1 is just 4. So we've got our horizontal asymptote at y equals 4. Okay, what else do we need? So we've found the horizontal asymptotes, no vertical asymptotes. Symmetry, again, don't really care too much about that, although I think this one actually does end up having some symmetry. We'll just skip that. We found the first derivative already in our previous video, so we'll go ahead and now use that to figure out our increase-decrease. So notice that the critical number here, I'm going to take the first derivative and set that equal to 0. But again, when we're doing that, it doesn't really matter what's in the denominator. I just set the numerator to 0, and that gives us a nice easy answer here, x equals 0. So that's critical. X equals 0 is critical. And so what do? When we only have one critical number. You can make a table here, but I'm actually just going to not do that because if there's only one critical number, all we really need to do is just figure out, well, what's the derivative to the left of that critical number? So let's say like -1, that would be like our test value. So if I take that and I plug it into the first derivative, notice the denominator is always going to be positive because it's squared. So if I have a negative number up on top, that means the whole thing is negative. So, and then I'll pick a number on the other side of 0, 1, and we'll notice that if I plug 1 in there, I get a positive number. So what does this tell us? Function is increasing on what interval? From minus infinity up to the only critical number, which was 0, and then it's decreasing on 0 to infinity. Nope, I think I have that backwards because the derivative was negative, so sorry, let me fix that. I should say decreasing there and increasing here. First derivative was negative, means the function is decreasing. So let me fix that. Okay, so first derivative negative means it's decreasing on this and increasing here. Okay, so we've got that, and the fact that that it did change from decreasing to increasing means that we've got a minimum value there. Decreasing one side, increasing the other, we've got a minimum. So minimum at, let's put that over here, at 0, and we already know what the y value is there, 0, 0. Okay, so we've got a y-intercept, x-intercept, and we've also got a minimum value at 0, 0. Let's do the concavity stuff now. So for the concavity, we need to set the second derivative equal to 0. Again, really all we have to do with these rational functions is just set the numerator to 0. So 32, 4 minus 3x squared equals 0. Well, again, the 32 is not going to matter. I can just divide both sides by 32. So I'm going to get 4. I'll have that equal to 0. And I could just move the 3x squared to one side and get 3x squared is equal to 4. Divide both sides by, let me try to separate this a little bit. Divide both sides by 3. Get x squared is equal to 4/3. Take the square root of both sides. Get x is equal to plus or minus the square root of 4/3. So that's 2 over the square root of 3. Okay, so there's our possible inflection points. So now we're going to have to make another table. This one we will do that because we've got 2 possible inflection points. So we'll go from minus infinity up to minus 2 over root 3. And then we'll go from minus 2 over root 3 up to positive 2 over root 3. And then we'll go from 2 over root 3 up to infinity. So there's our table for our concavity stuff. So we'll have a test values and the sign of the second derivative now. And we have our conclusion based on what we see in the table. So 2 over root 3, let me see what that is as a decimal so we can figure out what a good test value would be. So that is 1.15. So we're going to go, we'll go smaller than that. X equals minus 2. We'll pick 0 here, and then we'll pick 2 here. Okay, so now again, we're looking at the second derivative, and what we can also notice about the second derivative is that no matter what x is, that denominator is always going to be positive, right? Because if I plug any number in there, squaring it, it's going to make it positive. So that denominator is positive. So really the only thing that is going to determine the sign of the second derivative is just that term in the numerator. So notice that if I plug 0 in there, I get 4. Well, 32 times 4 in the numerator, that's a positive number, right? When I plug in either negative or positive 2, I'm going to get the same thing because that's squared. But notice, say I take a 2. 4 minus 6, that's a negative number, and I get the same thing when I plug in negative 2. So my conclusion here is the function is concave down, and then it's concave up, and then it's concave down. So notice we do have 2 inflection points here. They are at, actually let me, I'll have to squeeze the graph down here. 2 inflection points at minus 2 over root 3, and then f of that, f of minus 2 over root 3, and that we're going to have to plug that into the function. So remember, f of means right back here in the original function. So let's, I'm just going to put that in my calculator real quick. F of minus 2 over root 3. And I get 1 for my output value there, so I'm going to have minus 2 over root 3, 1. And then I've got another inflection point at positive 2 over root 3, and f of that. Notice that, again, since I've got those second powers there, it's going to give me the exact same output value. Oops, that one's not negative though. Positive 2 over root 3. Fix that. 2 over root 3 and 1. So I've got 2 inflection points, and I think that's everything we need. So let's go ahead and squeeze the graph down here. All right, so some important values that we found here. 0, 0 obviously is an important value. And then we've got these inflection points at negative 2. I'm going to make this negative 1 down here. I'm going to make this positive 1 over here. We found that those decimal approximations were about 1.15, about 1.2. So I know I'm going to have an inflection point at, let's call this 1 up here. Actually, no, I'm going to have to call that 4 because we've got that asymptote. Let's make this 1 right here. And got an inflection point at about 1.15, so a little bit, maybe about right there, I guess. We've got another inflection point about right here. Okay, so that's what we know, and we've also got this horizontal asymptote. That's why I wanted to make sure that we had that on there, 4. So there's our horizontal asymptote. Okay, now what do we have? What else do we have? The function is concave up between these 2 points that I have drawn right there. So concave up, kind of make a little upward shaped bowl right there for that part of it. Concavity changes right here at this point. It becomes concave down after that, and it has to approach that horizontal asymptote, so it's kind of hard to see it again, but you can kind of see it changes. Now it's like a downward shaping bowl as it approaches those asymptotes. So again, you can check this on your calculator, and then also just notice that the first derivative stuff held as well, right? What's the function doing? It's going down until we reach 0, and then it's going up after that. So graph it on your calculator just to make sure that you can see everything. Just bump this up to make sure everybody can see that graph. Okay, so these problems that have us graph stuff, as you can see, there's a lot of work involved here. We have to find both derivatives, and we have to do all of this stuff with the first and second derivatives. So kind of a bit of stuff going on there. But again, you know, taking this class online, totally welcome to use the calculator. Take your time, make sure that you get this right, and we'll move on.